All right, this is a question I get from time to time, and I thought it was a little overdue to answer it. It was people asking questions about what are bucking transformers, bucking windings. Help me understand this, and so that's what we're going to do today. I think this is going to be a fun one. Stay tuned. All right, I'm a firm believer if you're going to have a solution, you better darn well have a problem and that you're trying to solve. And so here's the problem. When a lot of the gear that we're using in our hi-fi setups was made, I'll just throw out some names: Fisher, Ico, Scott, things of that nature. When a lot of this older vintage gear was made, the line voltages to our house was a lot less than it is today. And I got this little statement here off of Wikipedia, so don't flame me if it's not 100% accurate. But up until the late 50s, line voltages to our houses were around 110 volts. And I went on to read that 110, 115, 117 volts were used at different time points at different locations across the country. And that similar stories exist in other countries where they've slowly over time increased the voltage feeding to your house. So the current standard is 120 volts to the meter outside of our house, and our U.S. regulations allow for that voltage to be up by 5% or down by 5% at any given point in time, which gives a range of 114 to 126 volts, right? That's seen at your meter box. These voltages can vary throughout the day. I use this little box here. It's called a kilowatt, about 20 bucks. You plug it in your outlet, and then you can plug your gear into it, but it'll tell you what the voltage is and a lot of other things too. Frequency, how much current that device is drawing. These are neat little devices to have. But I actually watch throughout the day sometimes, and I notice my line voltage here at my house varies from about 119 up to about 123. And thus I use devices like we're going to be talking about today to bring that voltage down. Here's a practical example. A tube amp that was designed to operate at 110 volts, but that's now running at 124 volts, right? Couple things that are happening. One, you're putting more voltage through this transformer, power transformer, running it a little hotter. Could produce some long-term issues for your power transformer. But more so than that, if you happen to be running a piece of tube gear, your filaments now, if you think about the relationship between the primary and the secondary windings feeding your filaments, as that primary goes up, the secondary goes up. So what was given 6.3 volts to the heaters of your tubes is now 7.4 volts. Will your amp work? Probably so. Will your tube life be drastically reduced? Absolutely. I could see it cutting tube life half, 2/3, maybe even 200 or 300%. So unless you're a fan of buying tubes all the time, I would not recommend running your filaments at 7.4 volts. Okay, so that's the problem we've got. Now let's talk a little bit about the solution. All right, so before we get into the solution directly, I do feel like we need to go over some transformer basics. For some of you guys, you might fast forward a little bit, but for others, it'll either be a good refresher or maybe you're learning something totally new here. On the left-hand side here, we've got the symbol drawn here in this little box for a transformer. And if you'll notice here, it has little squiggly lines on the left. That's representing the primary winding of the transformer. The little squiggly lines on the right are representing the windings on the secondary, and then the two little vertical lines there in the middle represent the transformer core. And the way a transformer works is you feed an alternating current into the primary winding. So you take an AC signal and you connect one end to one end of the primary winding, another connection to the other end of it, and you basically send that alternating current through that winding. And what it does is it works off of electromagnetic currents. And what it does is it induces a similar waveform or signal on the other side of the transformer. And so what happens is you feed something into the primary via AC and you get an AC signal out the secondary. Does not work with DC. Okay, direct current, if you feed DC, if you got your 12 volt DC power supply out or whatever, fed it into the primary of a transformer, all you are going to do is see the DC resistance of the wire, the windings in the primary and the wire, so the resistance of that wire, and you're basically just going to heat the transformer up. Not a good idea. But the way this works here, if you'll notice on the left, I've got something here denoted VP. That's voltage in the primary. And below that, I've got NP, number of turns in the primary. And then on the right-hand side, you have VS, voltage in the secondary, and NS for number of turns in the secondary. Those two, the relationship between those two is directly proportional, okay? So if the number of windings in the primary, and we got an example here, let's say we have 1,000 turns in the primary and 100 turns in the secondary, that translates to a 1,000 to 100 ratio, or a 10 to 1 ratio. So thus, if we fed 120 volts into the primary, we would get 12 volts out on the secondary. So that's the way this ratio works. If you're doing that, if you've got more turns in the primary than in the secondary, then what that is called is a step-down transformer. So we're stepping the voltage down from 120 volts to 12 volts. And if you had more windings in the secondary than the primary, it's a step-up voltage, okay? Now, with all electronics and all things in this world, nothing comes for free. So if you were to put 100 windings on the primary and 1,000 windings on the secondary, and you fed 120 volts into the primary, you'd get 1,200 volts out on the secondary. Woohoo! We're getting more out than we put in. Well, there's a trade-off. The current in the secondary also goes down by that same ratio. So the current is an inversely proportional ratio to the windings. Then current is a directly proportional ratio. Okay. Okay, so you're probably going, wow, transformers aren't that hard. I was able to grasp that. Well, understanding a transformer is pretty simple. Designing and building one, a whole nother story. And I'll give you an example. You could have a transformer with 100 windings on the primary and 1,000 windings on the secondary, and that would be a kind of a 1 to 10 step-up transformer, right? You could also have a transformer that has 10 windings in the primary and 100 in the secondary, and you'd have that same 1 to 10 ratio step up. And then you would be going, well, how many windings should I use then? Should I do the 10 to 100 or the 100 to 1,000? And that's where things get a little more complicated. So the size and length of wire used in the primary and secondary can affect how much power transfer the actual transformer can handle without damaging the windings. And also the metal characteristics and the physical size and shape of the transformer and the core can also affect the transformer, its efficiency, how easily the core saturates with these magnetic currents, causing it to overheat or not be as efficient. So there's a lot more to transformers. The good news is, for today's video, all you need to understand is what I talked about earlier, was a little bit of the windings ratio. Okay, just two more quick concepts here before we dive into actually one of these bucking transformers. First is about phasing. So if you notice here on this little transformer signal in the middle of these two voltmeters, you kind of got the windings on the primary, windings on the secondary there. You got the vertical lines that represent the core. And then you got these two little dots above it. And what those dots denote is the phasing of the transformer. So you could have a winding on the left-hand side and the right-hand side in phase with each other, or you could take that winding on the right-hand side and kind of flip it around, or in other words, just reverse the polarity of the leads feeding to it, and they would all of a sudden be out of phase. So what happens when your transformer is in phase? The secondary windings basically follow the primary windings from a waveform standpoint. If you'll notice here in the picture, as the sine wave goes up, on the left side, it goes up on the right side. Now, they may be at different amplitudes because of the difference in transformer windage. You could have a 10-to-1 here, and the waveform on the left would be 10 times bigger than the one on the right. But they would both go up at the same time, down at the same time. They would basically follow each other in something we call in phase. In other words, at a 0 phase angle. Okay, down here in the bottom picture, we show an out of phase transformer configuration. In other words, we flip the wires around on the secondary winding here on this transformer, and now they're no longer in phase with the first one. So when on the left picture here of the little voltmeter, when that sine wave is going up, it's going down on the other side. And as the sine wave is going down on the left-hand side, it's going up on the right-hand side. In other words, that is 180 degrees out of phase. In other words, these things are inversely mimicking each other. And that's as simple as reversing the polarity on the wires on this secondary set of windings here to take it 180 degrees out of phase. That's why a lot of transformers, when they mark them, they'll show you, hey, maybe the yellow wire is in phase with the blue wire, but if you flip it over and use maybe the white wire, it would be out of phase. So transformer little diagrams that come with them will have these dots to show in or out of phase. All right, our last little educational journey here will be about adding AC waveforms. Sometimes you'll see this termed in the industry adding complex waveforms. But what I wanted to show you here is on the left-hand side, let's say you had two signals of alternating current coming into the same point on a wire, okay? What happens if those signals are in phase with each other? They actually add to each other. So if you'll notice here on the very left-hand side, two signals coming into the same point, what starts to happen is they start to add to each other, and the actual output would be larger than the two pieces put together by the total of the sum of the waveforms at any single point in time. If you'll notice, the x-axis here is time on this, and the y-axis here is kind of amplitude or volts being measured. So as the signal's going up on both of these, they're getting added together into one larger signal down here at the bottom. But what happens when your signals are out of phase with each other? So you'll notice we've got two AC waveforms over here on the right-hand side. One of them's going down, the other one's going up. The net effect of those, you add them together at any single point in time across the x-axis, you get the net sum of those. So as you add up, I'll give you an example here on the bottom of this peak, minus 5 volts AC on the top one, plus 5 volts on the bottom one. Well, minus 5 plus 5, guess what that equals? 0 volts. And so if you have two sine waves 180 degrees out of phase with each other, you add them together, what you get is what you see in this bottom picture down here on the right hand side. You get a flat line, in other words, 0 volts out. That's very important to understand as we get into how this bucking transformer works. Then I've got a little picture down here on the right hand side that kind of shows, well, what if they're not equally matched sine waves? And this would be what I'd consider adding complex waveforms. You've got this nice sine wave at one frequency, you've got a nice sine wave down here in the second little picture at a different frequency. You add them together and you start to get this kind of the sum of each of the two at any given point in time, and you start to get this really odd looking waveform. Well, this is the result of adding things that are less than or more than 180 degrees out of phase. These two down here, the result of adding two different things at two different frequencies. But really what you got to remember is this middle picture here where I showed you adding two things 180 degrees out of phase. Ultimately, when you add those together, you get the net sum of that, which is 0 in this case. All right, based on that, there's a couple different solutions we could use, leveraging different types of transformers to reduce the voltage going to our vintage gear. The very first one, very commonly used by a lot of people, it's what I use here on the bench. You just use a variac. A variac's kind of a version of a transformer configuration called an auto transformer, and I'm not going to go deep into that. But basically you can see in the picture down here, what it is you've got your primary winding on one side, and then you got a secondary winding on the other side. But that secondary winding can be slid up or down with the turn of a knob. So you're actually changing the turns ratio as you turn your knob, more windings or less windings on the secondary. So if you have a fixed input of 120 volts, you may on the output get all the way down from 0 volts. And sometimes these things even have windings that go on up that would even let you put out more on the secondary than on the primary. In other words, you've added more turns to the secondary. So you may be able to adjust from 0 to 140 volts on the output. So why don't you just use a variac on every one of your pieces of tube gear around your house? Two reasons I can think of, well, three actually. One, they're not inexpensive. A good variac, usually $100 or more. If you find one used, maybe $50, $60, a lot of times they're kind of worn out because they were used in a lot of industrial usages, and there's a reason they came out of service. But if you were to buy a new one, you could be $100 to $200 in that case. Two, you could easily bump the big knob on the front of one of these, and all of a sudden you were planning to put out 110 volts, and the knob gets bumped, and all of a sudden you're putting out 130 volts. You're even doing more damage. And then the third one, these things are big. You know, they're big, heavy, weigh 30, 40 pounds, big devices. So just not all that practical, I guess would be one way of saying it. All right, next thing you could do is you could just go out and buy a transformer that has 120 volts on the input. It has a few less turns on the output, and it puts out 110 volts on the output. You're probably wondering, well, why the heck doesn't everybody just do that? Well, a couple of reasons. One, they're not all that commonly seen. They're not mass produced. If you were to buy one, it would cost you a good bit. And two, they're fairly large in size and kind of costly, like I mentioned. So while it seems to me the most practical answer, it's not the most commonly seen answer out there. And I've kind of highlighted here in blue what I think are the two most common answers out there. All right, first off, it would be an external bucking transformer. It is a cheap, or I'll say less expensive DIY alternative to number one or number two. And then the fourth option, while maybe a little more specialized, you could use an unset of windings in the power transformer of an old piece of vintage equipment, if it happens to have an unused set of windings, and we'll talk about that more in a minute. But you could use that to buck down the voltage on the secondary, and we'll talk about what that looks like. So those are the two items we're going to focus on today. All right, we're going to talk about an external bucking transformer. In other words, we're not modifying our piece of gear at all. We're putting a device between the wall outlet and our piece of gear's power cord to somehow reduce the voltage going to your piece of gear. Everything we've done thus far, I think, has been pretty easy to grasp. If not, ask me some questions. I'll try to give you some clarity. But this is where we take a little step up, where it gets a little more in-depth, and you got to kind of take a leap of faith and just trust that this is how this works. Okay, so the way it works is you take the secondary in a transformer, okay, and you wind it in series with the primary. And I'll show you down here in this example. So we've got a transformer that was originally designed to feed in 120 volts on the input and 10 volts out on the secondary. So it kind of has a 12-to-1 turns ratio, okay? And what we're actually doing here is we're going to wire that secondary in series with the primary. In other words, that 10-volt winding is actually getting added to the windings on the primary, except they're being wired out of phase. And we talked earlier about what happens when you have something out of phase. It starts to add at any given point on that waveform the sum of those 2 points. And if it's out of phase, it's likely to be negative relative to the primary winding. So the way this kind of gets viewed as we've got 120 volts into this thing plus minus 10 volts because it's out of phase, ultimately would give you 110 volts out in this scenario. So the way you wire this, you wire in into your primary transformer here just like you would any other transformer, 2 leads that go back to your wall input, okay? But on your secondary, instead of taking both of the windings and going to your output, you take one of those windings and you bring it back over and you tap it into the primary, in essence, and adding it in series to the primary, out of phase. And then you take your secondary, the other wire of your secondary, use that as your output along with the tap off of the bottom wire here on the transformer of your primary. And you take an output of that. It's somewhat of a variation of an auto transformer, but what this does at the end of the day here, just like the picture shows you, and you'll just have to kind of trust this a little bit if you're not totally following the phasing thing. 120 volts in, that 10 volts at the top is bucking against that 120 volts, and you're getting 110 volts out on the AC over here. Now, you may say, well, why do that instead of just buy a transformer that has 120 volt primary winding and 110 volt secondary winding? Well, there's a little bit of magic that happens with a bucking transformer here. And I'll give you the example here. If this was a 10 amp rated transformer, okay, for the secondary here, it would have to buck 10 volts at 10 amps or 10 volt amps, okay, to produce 110 volts on the output at full current. If you were to buy a step-down transformer, though, it would need to handle 110 volts on the secondary at 10 amps, or this would be a 110 volt amp transformer, or watt transformer. In other words, a much, much larger transformer. So somehow this little magic of the auto transformer and bucking against the winding lets you reduce the voltage without having an extremely large transformer. And I'll show you some pictures here in a minute that'll help you understand that a little bit. So one way you could do this, you could jump on eBay, Amazon, lots of places, and you could buy this little thing called a brown box, commercially available solution. So they've fancied it up a little bit. If you'll notice here, the top knob lets you select between your primary voltage here. And what it is, all they do is they've got multiple taps on the primary here, okay? And then they've got a reduction level switch down here at the bottom, okay, that lets you reduce by 3%, 4%, 6%, 10%, or bypass one. In other words, no reduction whatsoever. And they're achieving that by the transformer they're using has multiple taps on the output, okay? But it's wired exactly the way I showed the other one wired a minute ago. You basically, in essence, have these secondary windings, depending on which tap, determines how many turns in series with the primary, out of phase. So if you flip this over, even though these dots look like they're in phase, when you flip that to the other side, they're actually out of phase. And then based on the tap, that would determine the number of turns, thus the number of reduction. So they put a nice little handle on this box. They put a IEC input into it here, a fuse with a switch. They've got the little output jack on the top there. They also have a nice little meter feeding into this thing. Really slick little solution. I love everything about it except for one thing. It's a killer for me. These things cost $249. It's insane. And the reason I say that is I know what the parts in this box would cost to actually build. That's about an $11 or $12 little meter right there out of China. Those the fuse holder and the output jack, let's just say you've got another $5 to $10 in that. The two switches in here rated at AC levels, those are $2 or $3 a piece. You got some nice gold knobs here, maybe $2 or $3 a piece. Nice little box here, maybe $10. Then you got the transformer. Oh yeah, that handle's probably $1 at the hardware store. And then you got the transformer with multiple taps that they probably had custom wound by somebody in quantity for them. I'm guessing this thing's easily made for $100 or less with all these features, maybe even in quantity as cheap as $60. So I struggle with paying $249 for one of these, thus why I do not own one of them. You can make one yourself for way less than this, and I'm gonna show you some examples of that. Okay, I have to give credit to this drawing and the next one I'm going to use. I stole them off the web, and this guy Rob Robinette has a website out there, and he has these pictures on there, and you can just go download these yourself. So if you search for him or this Buckminster bucking transformer, this is a DIY solution. It's a little bit more complicated than the second one I'll show you. But if you'll notice here in this, you've got a little box you would buy at Lowe's. You've got a small little transformer. This is not a big transformer, and that is the beauty of the bucking transformer. You get by with a fairly small transformer like this. You got your little line here that feeds around and feeds into your wall. Then you've got your outlet here you would plug your piece of equipment into. And then you've got a switch here to turn this thing on or off or whatnot. Okay, so if you follow the schematic over here on the other side, you kind of come out of your power cord, you come in with one wire, he's bringing it up here. He's actually bringing it through a fuse, which is a smart thing, just in case your gear doesn't happen to have fuse. You bring it through there, comes into one side of the primary, and then the white wire over here kind of ties and goes into the other side of the primary, right? You coming out your secondary then, right? If you'll notice one side of your secondary there then is feeding back over into your primary, putting it in series like we talked about earlier. Okay, the other side of your secondary here is kind of coming over into a switch, which was this little switch right here, okay, that lets you either kind of put it in the middle off or switch it to one side, which would be minus 12% reduction. So he's then feeding out of that over here to one outlet. Then he's got the center tap here, feeding over to another spot here on the switch, which would only give you 7% down because it's at the center tap and not the full. Less windings added back in, out of phase with the primary, gives you less reductions, more windings. The full winding here gives you more. Then he's wiring it into a power outlet basically, and the only other thing he's done here is he's thrown a light switch across this thing so that when it's on you would know it's on or off. And it's a nice little case here. And then you would just throw a blanking cover over this other end down here, and you can see the switch on the side. That would be your nice little bucking transformer. I'm betting all the parts for this you could build for $40 or $50 here. Okay, and then here, same guy shows an even simpler version of that, where you're basically, you don't have all that switching going in. You're just feeding straight from the secondary to one of these, straight from the secondary to a second outlet, and you're kind of having to break the ties between the, he says here, you must break the hot link terminal. So on the side of a power outlet here, there's a little bar you got to break off to do this, because normally these things are tied together in the outlet. But basically you end up here with, if you plug it into this outlet, you get 12% reduction. If you plug it into this outlet, you get 7%, and you just don't have the switching. So this little outlet's going to cost you $2 or less. If you'll notice here, the transformer is a Hammond 166N12B 12-volt transformer. At 4 amps, it costs you $14. The little box you're going to put it in, probably $5 or $6. A power cord, another couple bucks. You're probably into this thing, probably 30 bucks at the most here. Great little solution. And you can see here at 125 volts in, you would get 116 volts out on this one, or 110 volts out on that one. You got 120 in, you'd get 112 and 106. And here's some pictures of how that little setup might look at the end of the day. One with the switch over here where you could kind of switch between them, and then another one over here that might have switching between them, or you could have done the one without the switch and just the two outlets. But you end up seeing how simple these little boxes look, and there's not a lot of money. You buy everything you need except for the transformer at your local Lowe's or Home Depot or whatever home improvement store you use, and then the transformer is simple enough to order off of Amazon, eBay, DigiKey, Mauser. Lots of different places carry those. All right, and last but not least, the second scenario where I see people, instead of having a bucking transformer, they're using some windings in an existing transformer to buck down the voltage feeding into a piece of gear. And I see this typically play out in two scenarios. One, you've got a console amplifier. So you took an amplifier out of an old stereo console, and you're now converting it over to be used as a standalone unit. Well, a lot of times the transformer in those amplifiers will have a set of windings designed to go over and feed the preamp, or maybe the tuner, AM/FM tuner, and that set of winding is not used anymore. So a lot of times you'll see people clip them off, kind of shrink wrap them and get them out of the way. Other times, depending on the voltage in your house or whether you need to buck your voltage down, you could use that set of windings to wire back in series with the primary out of phase and bring the voltage down for the rest of your amplifier. Okay. And then the second scenario I see used in this case is when you take an old amplifier of some sort and you convert it over from being tube rectified to solid state rectified. In other words, you remove the vacuum tube rectifier, 5U4, 5AR4, 5V4, whatever, 5Y3. You remove that, and now you instead put some diodes in there and do full wave solid state rectification. Well, then you've got a 5-volt winding left over, right? Well, you can now take that 5-volt winding, wire it over out of phase in series with the primary, and reduce the voltage to the rest of your amplifier. It's a great little thing to do. One little note I've got here, let's say you do that and you wire that 5-volt transformer winding back over in series with your primary, and your voltage doesn't go down, maybe it goes up on the output, then you've not got it right, the phasing right. Just take the two wires and flip them around and crank it up again, and you'll notice the voltage will go down, feeding your amplifier. And then I also made a note over here about this. The advantage of using a 5-volt winding, maybe doing away with the tube rectification and using this 5-volt winding, that 5-volt winding is a special kind of winding because it's got to be able to handle not only the 5 volts AC, but if you look at any schematic of a tube amplifier, you'll notice that it also has to carry the voltage off the cathode on the rectifier, which would be somewhere 400, 500, 600 volts a lot of times. So that winding gets tested usually at the factory with something called a high pot tester to make sure that the laminates in it don't break down at high voltage, and it turns out to be an excellent winding to use for bucking down. Personally, I like tube rectification, so I don't do that a lot. I would either use an external transformer or find another set of windings, but just wanted to call that out for you. So hopefully you've learned something here, and if you got any questions, post them below. I can always try to answer them there or even make a follow-up video. Sorry this is probably a 30-minute long plus video, but I felt I needed to explain it. I've seen a lot of things on the web about bucking transformers. I see a lot of people have questions about them. I did not see any good videos out here on YouTube explaining these things in depth. So you know me, I like to go deep. So that's what we did here today. And I'm going to leave you with one last thing. I'm still working on this single-ended KT88. If you're wondering why I'm throwing these videos in here in parallel, like this PowerPoint here, I can sit at my desk at lunch while I eat lunch or whatnot, make these, and then come home and record to them. Fairly simple and quick. I can't exactly carry the KT88 to work with me and sit there at lunch and build on it. So this gives me a way to burn some of my lunch time and bring you guys more content as a result. So still grinding away on it. You'll see something here soon on it, I promise. All right, one last thing. If you had a hard time reading this, I am going to save this PowerPoint out on my website under sketches and info, www.blueglow.net. You can go out there and download it as a PDF. And thanks again, you guys, for watching my videos. I know I can get a little long with them, but I love bringing you educational stuff like this, and I like to really try to cover the topics well. So hope you enjoy them, and thanks again for watching, everybody.